Okay, good morning Year 12. So we're just going to finish off our vectors topic by looking at modelling with vectors, and in particular on this one we're looking at resultant vectors. Okay, so the result of two or more vectors being added together. Okay, so there's a few examples that I want to look at. This one again was of the AQA teacher guidance, so it's one they're thinking you should know, so we'll go through this to start with. So we've got two forces, P, which is 6i minus 3j newtons, and Q, which is 3i plus 15j newtons, act on a particle. Okay, and it's just reminding us that I and j are perpendicular, so I is obviously going in the horizontal positive x direction and j goes in the positive y direction. Okay, so when we say things are acting on particles, they could be pulling or pushing the particle, it doesn't matter, but they need to be doing this, both of them together. Okay, so the picture I've got here is, here's the particle, and both Q and P are pulling the particle, but what is the overall effect? Okay, if P is acting in this direction with this magnitude and Q is acting in that direction with a different magnitude, what happens to the particle? Okay, does it end up over here? Does it end up over here? Or does it end up somewhere in between? Okay, so the way to consider this is actually to think about the two forces acting at separate times. So we could say that we could pull the particle in this direction and then apply force Q. So what would happen then is that this force would join on to the end of force P. Okay, so I would do force P and then I would do force Q, and the particle would end up here. So this vector that I'm going to draw in now, okay, which I think I'm going to make red, okay, is the resultant vector. Okay, so this bit here is what ultimately happens to the particle that we started with. It started here, it ended up here. Okay, how did we get there? Well, we went along the P vector and then along the Q vector, so we are adding those two vectors together to get to this point. So remember, it doesn't matter which route you take with vectors, okay, it will be the same whichever route you took, this resultant vector will be the same. So let's have a look then at what this vector would be. We would call this vector P plus Q. So this is the vector P plus Q. Okay. All right, because we've gone along this one and then that one. So we are asked to state the resultant of P and Q, which is P plus Q. So we've been given the two vectors and I'm going to add them together. So we had 6i minus 3j plus 3i plus 15j, and that's in newtons. Okay, so we've got 9i's and 12j. So the resultant of P and Q is 9i plus 12j. Okay, then we're asked to calculate the magnitude of the resultant P and Q. So remember, the magnitude is the length, and we use Pythagoras to help us calculate that. Okay, so if we imagine our triangle, here's my resultant vector here, it would be 9i's plus 12j's, so that would be 9 squared plus 12 squared square rooted, and that would give you 15 newtons exactly. So I know the magnitude here is 15 newtons. Okay, we're then asked to calculate the direction of the resultant of PQ. So we're looking for this direction. If you remember, we tend to measure the angle of direction in relation to the positive x-axis. So here's the positive x-axis, the I direction here. I'm looking for this angle here. Okay, so we know the opposite is 12, we know the adjacent is 9, so we can use the tan ratio. We'd have inverse tan of 12 divided by 9 gives you 53.13 degrees. Okay, and that is going anti-clockwise from the positive y-axis. So I'm just going to scroll back to the top because there was a note in the teacher guidance that I want to refer to. So it does say, note when answering part C, which is the calculate the direction, students will be expected to be specific about where they are measuring their direction from. So this can be done with a clear diagram or described as 53.1 degrees from the I direction, for example. Okay, so on my diagram, I would probably want an arrow in there to say I'm going that way, or I would write 53.1 anti-clockwise from the positive X or the I direction. Okay, so just again, making sure you're very clear about what the angle is that you're measuring. Okay, so this question again was on the teacher guidance for the AQA, so I thought it was worth having another look at. So what we've got here are three forces, okay, which act in the same plane. Okay, so we're not looking in 3 dimensions, we're just looking at 2 dimensions, and are in equilibrium. So the key word there is equilibrium, and if things are in equilibrium, okay, there is no overall effect. Okay, so the resultant is 0, or another way of thinking about it is you end up back where you were. Okay, so what we've got here, we've got the forces for this one coming down here is 5 newtons, this one going across here is 6 newtons, but we don't know the force for F. Okay, so we're asked to find F initially. So we know these 3 forces are in equilibrium. So in other words, if I travel along F and then I add this one to it, I would end up at this point here. If I then add this one to it, I would end up, like I said, back where we started. But we've got a nice right angle triangle now, so let's just write in, this force here was worth 6 newtons, and this force here was worth 5 newtons. So in order to work out this force in newtons, I need to use Pythagoras with 5 squared and 6 squared summed and square rooted. So here we have 6 squared plus 5 squared, square root of that is root 61. So, and that again is in newtons. So it's root 61 newtons, so you could work that out as a decimal, okay? And we'll write that in there, root 61 newtons. So the size of that force is root 61 newtons. We're then asked to work out alpha, okay? And again, we can see we've got a right angle triangle, okay? We're shown here that that's a right angle, which means this here must be a right angle. So it's just again using the tangent, opposite over adjacent, and inverse tan to work that one out. Okay, so inverse tan, opposite over adjacent is 5/6, will give you 39.8 is alpha. Okay, and again, we're given the angle that we're expected to work out, so we don't need to worry about explaining the direction on that one. Okay, so key word there was equilibrium, just that you end up back where you started. Okay, example 3. So this is a classic question, but it is slightly different to the other 2. So we're going to have to think really carefully about this one. Okay, so on the previous 2 we were adding vectors together to find a resultant vector. On this one we know the resultant vector and we've got to work out one of the missing vectors. So let's read the question. We've got a man wants to swim across the river. The current is flowing at 1.8 meters per second. So I've drawn that in there, and that's a velocity vector there. Okay, and we know the current is flowing parallel to the riverbank. So here I've got my 2 riverbanks here and here, and the current is flowing in that direction parallel to the riverbank. Okay, so find the speed and direction he needs to swim at for his resultant speed to be 1.2 meters per second perpendicular to the riverbank. So the resultant we're given we need to find out one other vector so that we have this resultant. So in other words, the man is starting here and he's going to swim and he wants to end up here perpendicular to the, so the vector is perpendicular to the riverbank. So let me just draw that one in red. This is our resultant here, from here to here. Okay, and we want that to be a vector of 1.2. Now if you think about it, if the man just started swimming and swam in that direction, okay, where's he going to end up? Well, he's not going to end up here because this flow of the river is going to drag him in that direction. If he wants to end up here, he needs to be swimming in this direction. Okay, so let's pop that up there. So he would be swimming in that direction, and the river would be pulling him, or the current, sorry, would be pulling him in that direction, so he would end up there. Now he wouldn't swim across there and then the current suddenly pull him across there. Of course it would happen gradually, okay, but as we said before, we consider the two vectors separately. We would assume that he would do this first and then this. Okay, so what are we looking for? We're looking for the speed and direction he needs to swim at for his resultant speed to be 1.2 perpendicular to the riverbank. So perpendicular means that we have a right angle here. Okay, all right, I'm just going to move that up a little bit. Okay, but you can see the idea that we've got a right angle triangle here. Okay, so we know that's 1.2. We know that's 1.8. Okay, I need to work out this one here, which I can do using Pythagoras. So, typing that into the calculator, 1.2 squared plus 1.8 squared square rooted gives me a velocity of 2.16 meters per second, or a speed, sorry. The speed is 2.16 meters per second. So now I need to work out the direction. So again, as we said before, as long as we're clear which direction, how we define our direction, it doesn't matter which angle we calculate. So I'm going to start by looking for this one because it's within the triangle, but then I might actually describe this angle in a minute in terms of he's swimming this angle from the bank. Okay, so let's have a look at this angle. I'm going to use the two bits of information I was given in the question, so 1.2 and 1.8, okay, rather than this one I've calculated out because I know that's rounded. Okay, so this is my opposite, this is my adjacent, so I'm going to be doing tan or inverse tan of 1.8 over 1.2. So let's just get that up. So if we do shift tan, and we're doing 1.8 opposite over 1.2. Okay, and we'll close that bracket, and we get that the angle is 56.3. Okay, so the speed is 2.16 meters per second. This angle here is 56.3. If I want to know this angle here, I would do 90 minus it. So I'll just write that in so I know. So it's 33.7. So to finish off, we would write that first of all he must swim upstream, okay, opposite to the current, at a speed of 2.16 meters per second and at an angle of 33.7 degrees to the bank. Okay, just put the degrees in. Okay, so the angle we're referring to is 33.7 to the bank. Okay, you could have written it as at an angle of 56.3 to the perpendicular. Okay, either would be correct, but again, as long as your diagram is clear and your wording is clear, that doesn't matter. So this is a classic question. It comes up in all sorts of forms, so you could have things like aeroplanes and wind speeds, but again, with all of these, you must draw a picture and just make sure you understand which the resultant vector is. So for this one, we knew the resultant vector, so it was the other two vectors that I needed to add together. Okay, and it was this one we needed to find out. Okay, so have a go at exercise 3.2. And then you should also be able to do exercise 3.3, but if you're not sure, have a look at the example just above it.